Hey guys, welcome to this free lesson on Rolle's theorem. So if you've never watched one of my videos before, when you are prompted, you want to pause and try the examples. And I always have free guided notes available for these lessons if you want to follow along. So to begin, let's state Rolle's theorem. So I'll read it out to you, and I highly recommend that you write this down. Suppose f of x is continuous on the closed interval from a to b and is differentiable on the interior of a to b. If f of a equals 0, which also equals f of b, then there is a c in a to b where f prime of c equals 0. Okay, so the thing I usually recommend with this is write all of this down and then take a moment to really read it over and think about what is this trying to say. Your goal here is to see if you can actually draw a picture of this. Because the reality is that this makes total sense, but this is totally written in, we've got a lot of technical math stuff in here, so we just kind of want to break this down and make sure we have a better idea of what this means. So what does this mean? So remember that this is saying that, so it's continuous, so that's something we want to remember, and then it's differentiable. So we know what things are continuous, we know what things are differentiable, and this is one of the key things, right? F of a equals f of b, which all of that equals 0. So let's think about ways that that can happen first. So let's pretend that we're going to do this in two different ways. So here's an a to a b, and here's an a to a b. So you know that a to b, f of a and f of b have to be equal to, they both have to equal 0, right? It says f of a equals 0 and f of b equals 0. So what that means is that I have to have these points here for sure, right? So what I want you to do is, if you're playing along at home here, try to draw some situations that would kind of happen with this and hit play when you think you've got it. Okay, so one way that this could occur, I could have some sort of graph going through here like this, and it kind of does whatever, but then it eventually comes back down to b. So this is one way I could have f of a and f of b equals 0, and then we've got some stuff in between. Notice this is still continuous, and it's definitely differentiable, so we're good to go there. And really, any other graph that you might draw like this it's kind of the same idea. But one other graph that would be kind of unique is if I were to just create a straight line from a to b. Okay, so now let's remember, what is this saying? This says that when that happens, there has to be a c where f prime of c equals 0. So what does it mean for f prime of c to equal 0? Well, it means that it has really a horizontal tangent, right? So if I look at my two graphs, so think about where the horizontal tangents might occur in this situation. I just drew something totally at random, right? But I would have a horizontal tangent right here. It would look like this. And I'd also have one right here, right? So I actually drew a situation where we had more than one c, and actually we have one more down here. All of these are horizontal tangents. So what Rolle's theorem is saying is that you're either going to have a situation like this where, your graph has got to kind of go up. It could either just go up and come back down, or it can go up and down like this, but this will definitely have a horizontal tangent. Or you have this other situation where you have this constant, and we know that the derivative of any constant is just equal to 0. So then the tangent of this would just be a horizontal line all the time. So that's what Rolle's theorem is trying to get at. So how do we use this? Well, one question that comes up that is kind of a strange way to think about Rolle's theorem, but it's totally Rolle's theorem, is this problem here. Show x cubed plus 4x plus 2 equals 0 has exactly one solution. So notice in how this question is being asked, this is not asking you for what is the solution. It's just asking you to show that there is a solution. And this would not be something that you could easily solve, right? This is x cubed. So this is actually a whole other question asking what are the solutions, but saying just how do you know it has one solution? So let's think about this. The first thing that we want to do is just determine whether or not this has a solution. And notice that the solution will make this equation equal 0. That's what this actually says. So this is the same thing as saying it has a root. And if it has a root, then that means it has just one x-intercept. So those are all things that kind of go hand in hand. So I'll just kind of write that down. So you could have the concept of the root, the solution, or the x-intercept. All of these terms kind of go with this equation up here because this equation equals 0. So these are all kind of the same thing actually in this context where this equals 0. So first things first, we want to use the intermediate value theorem. And what I mean by that is we want to think about just a couple of values with this. And if you forgot the intermediate value theorem, don't worry, I'll remind you what it is in a second. So first things first, let's just pretend for a second that I have this function f of x just equal to this, okay? So what I want to do is I'm just going to kind of play around here and plug in a couple of numbers at random so that I can notice some behavior. So if I plug in f of 0, so what do I get? I get 0 plus 2, so this will equal 2. And then I'm going to also plug in f of negative 1, and notice what I get here. This would be negative 1 minus 4 plus 2, so this would equal negative 3. Okay, so now what I want to do is I want to just notice something here. The intermediate value theorem says if you have this behavior going from positive to negative, then that means that there is a root in between. So somewhere between 0 and negative 1, there has to be some solution in here that would make this whole thing equal 0. Now again, we're not being asked to find that value, but now we know that absolutely for sure somewhere between 0 and negative 1, there has to be a root. So let me note that. I would recommend that you kind of write all of this down, and then I'm going to summarize this for us. So let me clear some space here. Okay, so I just wrote this down. The solution is somewhere between 0 and negative 1 by the intermediate value theorem. Okay, so now here's what I'm worried about. I'm worried, let's just note, here's 0 and negative 1. Let me give myself more space than that so I can really exaggerate this. Here's 0, here's negative 1. So as it stands, I think that this equation might work something like this. But what I'm worried about is, so maybe it just goes like this and continues down this way for forever. But what could happen, right, something that could happen is somewhere between 0 and negative 1. Let's say that this equation goes something like this. So think about why this actually matters. What we're being asked to do is show that there is exactly one real solution. If this situation were possible, then there would be a lot more than one real solution. Just in how I've drawn this, I have 1, 2, 3, 4 solutions, right? So I want to make sure that this situation I have here, that maybe this is the only thing that can happen. It's not going to turn somewhere in this interval. So this is now where I'm going to use Rolle's theorem. So let me clear this off. And so think about this situation for a moment. Let's assume the worst case scenario and assume that there is more than one real solution. So we have something like this. Okay, if that happens, then that means that we can use Rolle's theorem. So I'm going to say, suppose there is more than one real solution. Well, let me clear off this. So then we can use Rolle's theorem. Now, by Rolle's theorem, what that would mean is there is some point, there would actually be at least 2 points that would equal 0. So I want you just to appreciate the logic of this. I started out saying I need to show that there's exactly one solution. The way that I'm going at this is I'm saying, let's pretend that there is more than one solution. This is a really common proof technique to assume the exact opposite of what you're trying to prove. The idea behind this is if I can prove the exact opposite of this and prove that that's not true, then I will, by logic, I will have proven that I actually have just the one. So I'm assuming that I have two places then where f of a and f of b equals 0. So two solutions really to this. Well, now we have to think about what would happen if I actually used Rolle's theorem. So let me give myself some space. And now I just want to take a second to think about what did Rolle's theorem say. So I am supposing that I have this condition here, right? I have an f of a and an f of b and both these equal 0. So according to this then, there must be a c where the derivative will equal 0. So this is what I should be able to find. So if that's what I should be able to find, well, you knew at some point we were going to have to take a derivative in this, right? So if I take f prime of x, so let's see what this gives me. This gives me 3x squared plus 4. So now what I should, in theory, be able to do is set this equal to 0. So I'm going to set this equal to 0 and I'm going to solve it. So look at what happens when you solve it. You get x squared equals negative 4 over 3. And check out the issue with this. If you try to solve this, you get an imaginary number. So this has no real solutions, right? Because the second you take x equals plus or minus the square root of not plus this, minus 4 over 3, now you can see that you get an imaginary number. So this is not possible when we are just looking for one real solution. So what I'm saying is this doesn't work, which means then, if you go back to what Rolle's theorem said, the whole thing about a theorem is that it has to work. So it's not like I can say, oh, I found a case where Rolle's theorem doesn't work. It's a theorem. It has to work. So instead, since I can't find this c does not exist, what that means then is I must have made a bad assumption. So I said that we have more than one solution, so I made this assumption, and then Rolle's theorem broke. So there must not be more than one solution. So let me clear some space. So we made a bad assumption. So our assumption was wrong. So what that means then is we must only have the one real solution, and we know that there was at least one that was guaranteed by the intermediate value theorem. So the way that this whole argument started, we knew that there had to be one. We just wanted to rule out if there was more than one. And by trying to use Rolle's theorem and effectively breaking Rolle's theorem, we had to conclude that we made the wrong assumption. There's only one solution. Therefore, this must not be true. So you can see this is kind of a lengthy, difficult argument, but if you take your time and really think through the details, you can get through this. So now we're going to take a look at another example. It's kind of a similar idea. But there's a plot twist with this. So the thing with these types of problems, it's not like an algebra problem where you just follow some algorithm to solve this. You are going to have to think pretty critically about this. So I will tell you this much. You can't start this off in a very similar manner, but there's going to be a little bit of a plot twist here, and I want you to try to sit with that plot twist and really try to think about what you know so far about some of these functions. So pause the video and then hit play when you're ready to see some of the solution. Okay, so in this one, I've kind of thrown you a bone here in some ways because you can use these values here to just kind of see what you get here. So if I take f of negative 2, let's see, I get 16 minus 2 minus 2, so this is just 12. And then if I take f of negative 1, I get 1 minus 1 minus 2, so I get negative 2. Yeah, negative 2. I swear I can do math. So now, in looking at this, so you have that positive to negative type behavior. So you know somewhere between -1 and 2 there has to be some value that will make this whole thing equal 0 by the intermediate value theorem. So we know that there has to be at least one 0 thanks to the intermediate value theorem. So let me clear some space and write that out. All right, so now we're going to do something similar like we did last time. So I want you to really visualize what are we trying to get at now. So here's my graph, and I don't know what this looks like, right? So a couple of possibilities that could occur. Here's -1 and -2. So think about what we're trying to say here. What we want to show is that we just have something like this, right? Where the graph is just going to go through once. But what we have to kind of rule out here is that I don't have something that's doing something like this, where the problem is this would give me multiple zeros in that interval. I want to have just the one 0. So the idea here is the same. You assume what happens if you have multiple zeros. So let me clear this out. And we assume the worst. So not really the worst, I'm just being silly, but so assume there is more than one 0. So if that's true, then we know we can use Rolle's theorem, right? So then maybe we try to use Rolle's theorem. So if I try this, I know I'm supposed to take the derivative, and this will equal 4x cubed plus 1. Now here's where the plot twist is going to come in. The Rolle's theorem tells me that I have to have a value where this derivative would equal 0. So if I set this guy equal to 0, then I totally can solve this actually. This is not a problem. So I get that x is equal to the cube root of -1/4. That exists, it's some decimal, but the thing is that this totally exists. Now this is where we have to start thinking a little critically and a little differently here. So Rolle's theorem didn't necessarily help us in this case. And if you think about what this value is, this value is going to be something probably closer to 0. So it's not actually even in the interval. So even though we found this, it's kind of like, okay, so now we've really got to think a little bit more about just this interval and the derivative. There's got to be some other solution in here. So let me clear out some space. And let's think about this a little bit more. So now we got to think about what we know about derivatives. What can I say about the derivative on this interval here? Can we say anything? Well, let's just take a look. Let's do a little exploration here. What will this equal? F of -1 would give me -4 plus 1, so this is -3. And f prime of -2, what would that give me? Well, it's going to give me, let's see, that'll be -8 times 4, so this is -32 plus 1, so this is -33. All right, so I can see here that this is going to give me negative values, and really if I plug in anything else in between -1 and -2, these are all going to be negative. What does that even mean? Remember, we're talking about the derivative here, so the interpretation of this is different from if I just plug this into a function, right? So that when you're talking about derivatives, you really now want to think about things like slopes. So these are negative slopes at these points, right? So if these are negative, then anything else in there will also be negative. And if the slope is negative, then what does that mean about the function? It means that the function is always decreasing. Okay, so who cares? Why does that matter? So think about what it means for a function to just always be decreasing. Maybe we should draw a picture of this. So make sure you've written this down. I'm going to clear out some space. So if I draw this again, here's -1, here's -2. So this has to always be decreasing. So think about what that looks like then. It just has to go like this. So we have actually ruled out the possibility. Remember, we were worried about this scenario. This can't happen because this would go from decreasing to increasing to decreasing. And we just talked about in this interval from -2 to -1 that this has to just always be decreasing. So this is the only situation that we can actually have. So that's kind of a little bit of a plot twist in the type of thinking that you're going to have to do when you work on problems like this. So then what we'll write here is, so then what we can say is that the derivative is always negative on this interval. So that means that the function itself is only decreasing on this interval. So if it's only decreasing, well, we know that a 0 has to exist by the intermediate value theorem from up here, but we also now know that only one 0 exists. So like I said, kind of a tricky argument. So thanks for watching, and I have a lot more other videos, so I'll see you guys in another one. Thanks for watching.